Welcome and introduction. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today, we embark on a deep dive into the cryptographic heart of modern web security. We'll explore the mathematics behind the HMAC-based Key Derivation Function, or HKDF, and see how it forms the backbone of the TLS 1.3 protocol. Our journey will take us from a single shared secret to a full suite of secure encryption and authentication keys, and we'll walk through a detailed example step by step. The genesis. Session keys. Let's start with a fundamental concept: session keys. When you connect to a secure server, you use public key, asymmetric, cryptography, like Diffie-Hellman, to agree on a shared secret. This process is amazing, but it's computationally slow. You wouldn't want to use it to encrypt every single packet of data. Instead, we use that initial shared secret to generate a new set of temporary, symmetric keys called session keys. Symmetric encryption, like AES, is incredibly fast and efficient, making it perfect for encrypting the bulk of our communication. The entire process of generating these high-speed session keys from the initial, slow-to-create shared secret is the core problem that HKDF solves. The key management problem. In cryptography, one of the fundamental challenges is key management. Imagine you and a server agree on a single secret key. Can you just use that one key for everything? The answer is a resounding no. Using the same key for multiple purposes is incredibly risky. For example, a key used to encrypt data from client to server should be different from the key used for server to client traffic. Furthermore, keys for encryption should be different from keys for authentication. Reusing keys can create subtle, and sometimes catastrophic, cryptographic vulnerabilities. This creates a critical problem. How do we efficiently and securely generate multiple, independent keys from a single, initial shared secret? This is the problem that key derivation functions are designed to solve. What is a key derivation function? A key derivation function, or KDF, is a fundamental tool in cryptography. Think of it as a cryptographic factory. Its job is to take an initial, shared secret, which we call the input keying material, or IKM, and transform it into one or more new keys. These derived keys are then used for specific cryptographic tasks like encryption or authentication. The goal of a KDF is to produce keys that are cryptographically strong, even if the initial secret has some weaknesses. It ensures that the output keys appear completely random. Crucially, knowing one of the derived keys tells you nothing about the original secret or any of the other derived keys. This property of key independence is vital. Enter HKDF. Among the many types of key derivation functions, the HMAC-based Key Derivation Function, or HKDF, stands out for its simplicity, efficiency, and strong security proofs. Standardized in RFC 5869, HKDF is not some brand new, experimental algorithm. It is a well-vetted, trusted standard in the cryptographic community. Its name reveals its core component, HMAC, which stands for Hash-Based Message Authentication Code. By building upon the solid foundation of HMAC, which itself is built on standard hash functions like SHA-256, HKDF provides a robust and reliable method for key derivation. Its elegant design makes it an ideal choice for modern protocols, for example, TLS 1.3. Why TLS 1.3 chose HKDF? The designers of TLS 1.3 made a deliberate choice to simplify and strengthen the protocol. A key part of this was adopting HKDF for all key derivation tasks. In previous versions, like TLS 1.2, the key generation process was more complex. It involved a function called the PRF, which mixed different hash functions in a complicated way. HKDF offered a much cleaner, more unified approach. Its two-step, extract then expand, model is easy to analyze and has very strong security properties. It is efficient to implement in both hardware and software. By using HKDF exclusively, TLS 1.3 ensures that its entire key schedule is built on a single, proven, and powerful cryptographic primitive. The core principle: extract then expand. The genius of HKDF lies in its two-stage design. The first stage is extract. Its goal is to take the initial shared secret, which might not be perfectly uniform or random, and concentrate its cryptographic strength. You can think of this as distilling a raw material to get its purest, most potent essence. This step produces a fixed-length, high-entropy pseudorandom key, or PRK. The second stage is expand. This stage takes the highly concentrated PRK and uses it as a master key to generate multiple, distinct keys for various purposes. This is like taking that pure essence and using it to create a variety of different, specialized tools. This separation ensures that even if the initial input isn't perfect, the final keys are strong and secure. The hash function. To really understand HKDF, we must first understand its fundamental building block. A cryptographic hash function, like SHA-256. A hash function is a mathematical algorithm that takes an input of any size and produces a fixed size output, known as a hash or a digest. For SHA-256, this output is always 256 bits, or 32 bytes. Crucially, it must be a one-way function. It is easy to compute the hash from the input, but it is computationally infeasible to do the reverse, to find the input from the hash. This property is what makes it useful for cryptography. Even a tiny change in the input, like flipping a single bit, will result in a completely different hash output, a phenomenon known as the avalanche effect. HMAC. The next building block is HMAC, hash-based message authentication code. While a regular hash function can verify data integrity, it cannot verify authenticity. Anyone can recalculate a hash. HMAC solves this by introducing a secret key into the hashing process. It essentially creates a keyed hash. An HMAC provides a way to verify that a message came from a specific sender who knows the secret key and that the message was not tampered with along the way. HKDF uses the HMAC construction, not for message authentication, but because of its excellent cryptographic properties as a pseudorandom function, or PRF. It is a way to mix a secret key and some data to produce an output that looks totally random. How HMAC works: a closer look. Under the hood, HMAC is more than just hashing a key and a message together. It is a two-step process that protects against various attacks. First, it combines the key with an inner padding constant, or IPAD, and hashes that with the message. Then, it combines the original key with an outer padding constant, or OPAD, and hashes that with the result of the first hash. This inner and outer hashing structure is what gives HMAC its strong security properties. You don't need to memorize the exact formula, but it's important to know that HMAC was specifically designed to securely mix keying material with data, which is exactly what we need for a key derivation function. HKDF extract. The formula. Now, let's look at the math of the first stage. The HKDF extract formula is elegantly simple. PRK equals HMAC hash, with salt and IKM as the inputs. Let's break this down. The hash is our chosen algorithm, typically SHA-256 for TLS 1.3. IKM stands for input keying material, which is the initial shared secret. The HMAC function takes two arguments, a key and a message. In this step, the salt acts as the HMAC key, and the IKM acts as the message. The output of this single HMAC operation is the pseudorandom key, or PRK. This PRK is the cryptographically strong master key that will be used in the next stage. Dissecting the inputs. IKM. So, what exactly is this input keying material, or IKM, in a TLS 1.3 handshake? The IKM is the shared secret that the client and server agree on using a key exchange algorithm. In modern cryptography, this is almost always an elliptic curve Diffie-Hellman, or ECDHE, key exchange. The beauty of ECDHE is that it allows the client and server to calculate the same secret value over an insecure network without an eavesdropper being able to figure it out. This resulting shared secret from the ECDHE process becomes the IKM that is fed directly into the first step of HKDF. Its quality is the foundation of the entire session's security. Dissecting the inputs. The salt. The salt is another critical input to the HKDF extract step. A salt is a non-secret, random, or pseudo-random value. Its primary purpose is to ensure uniqueness. By using a different salt, you will get a completely different PRK, even if you use the exact same IKM. This is a defense against pre-computation attacks. An attacker cannot just create a giant dictionary mapping common shared secrets to their resulting keys, because the salt changes the output every time. In TLS 1.3, the initial salt is derived from previously generated secrets in the key schedule, or it can start as a string of zeros if there is no prior secret. The output is PRK, which stands for pseudorandom key. The result of the HKDF extract step is the pseudorandom key, or PRK. This key has two very important properties. First, its length is fixed and is determined by the output size of the underlying hash function. For example, if we use SHA-256, the PRK will always be 32 bytes long. Second, it has high cryptographic entropy. This means it is computationally indistinguishable from a truly random string of the same length. The extract step has effectively purified the initial shared secret, removing any potential biases or weaknesses and concentrating its randomness into this single, powerful key. HKDF expand. The formula. Once we have our strong PRK from the extract stage, we move to the expand stage. This is an iterative process designed to generate as much keying material as we need. The formula looks a bit more complex, but the idea is a loop. We generate blocks of output, T1, T2, and so on. The first block, T1, is calculated as HMAC hash, using PRK, info, and the hexadecimal value 0x01. Subsequent blocks, Tn, are calculated by feeding the previous block back into the function HMAC hash, using PRK, Tn-1, info, and the hexadecimal value 0x0n. Finally, all the generated blocks are concatenated together to form the final output keying material, or OKM. This is then sliced up to create our keys. The iterative process explained. The iterative nature of the expand step is key to its ability to generate a long stream of pseudorandom bytes. The process starts with an empty string, T0. The first block, T1, is generated using the PRK, some context info, and a counter byte of 1. For the second block, T2, the process repeats, but this time, the output from the first block, T1, is included in the input for the HMAC function, along with the info and a counter byte of 2. This chaining mechanism, where the output of one step becomes part of the input for the next, ensures that every block of the output stream is cryptographically linked to all the preceding blocks. This prevents an attacker from being able to predict or manipulate any part of the key stream. Dissecting the inputs. The PRK. In the expand stage, the role of the PRK changes. In the extract stage, the IKM was the data, and the salt was the key. Now, in the expand stage, the PRK, our highly concentrated, pseudorandom key, becomes the key for the HMAC function. This is a crucial design choice. We are now using our strongest, most random secret as the key for the HMAC algorithm. The data being authenticated is a mix of the context info, the counter, and the previously generated block. This leverages the security of the HMAC construction to its fullest. ensuring the output is also strongly pseudorandom and unpredictable. Dissecting the inputs. The info parameter. The info parameter is arguably the most important input for security in the expand step. Its purpose is to provide context binding. This means it cryptographically binds the derived key to a specific application or purpose. The info string contains information describing what the generated key will be used for. For example, when generating a key for client-to-server traffic, the info string will be different from the one used for server-to-client traffic. This ensures that the two keys are completely different and cannot be mistaken for each other, even though they are derived from the same PRK. This prevents a whole class of cross-protocol attacks and is a cornerstone of good cryptographic design. The HKDF label structure in TLS 1.3. To ensure consistency and prevent errors, TLS 1.3 defines a very specific structure for creating the info parameter, called the HKDF label. This structure is not just a simple string. It's a carefully constructed sequence of bytes containing three fields. First is the length of the key we want to generate. Second is the label itself, which is a string prefixed with TLS 1.3 to avoid collisions, like TLS 1.3 client traffic key. The third, and most critical, is the context, which is a hash of the entire transcript of the handshake messages exchanged so far. This binds the key not just to a purpose, but to this exact, unique communication session. The output is OKM, standing for Output Keying Material. The final result of the HKDF expand step is the Output Keying Material, or OKM. This is a long string of pseudorandom bytes. The length of the OKM is determined by how many keys we need and how long they need to be. If we need a 16-byte key and a 12-byte IV, we would run the expand step until we have at least 28 bytes of OKM. The protocol then simply slices this OKM into the required chunks. The first 16 bytes become the key, and the next 12 bytes become the IV. This straightforward process of generating a long stream of keying material and then cutting it up as needed is both efficient and secure. Example. Let's derive a key. Theory is great, but let us walk through a concrete example to see exactly how this works. We are going to manually perform an HKDF key derivation. Our goal is to derive a 16-byte, 128-bit encryption key and a 12-byte, 96-bit initialization vector, IV. To do this, we need some initial inputs. We'll define a sample input keying material, IKM, which would normally come from a Diffie-Hellman exchange. We'll also define a salt value and an info string to describe the purpose of our derived keys. Let's get started. Example. Our inputs. For our example, we will use the following inputs. Our IKM, representing the shared secret, will be the simple ASCII string shared secret. Our salt, a random value, will be the string random salt. Finally, our info string, providing context for the key we are deriving, will be a ES128 GCM key IV. We will also use the SHA-256 hash algorithm, which is standard for TLS 1.3. Remember, in a real-world scenario, the IKM in SALT would be raw bytes, not printable strings, but we are using strings here for clarity. HKDF extract. Our first step is to perform the HKDF extract operation to create our pseudorandom key, PRK. The formula is PRK equals HMAC-SHA-256 of SALT, IKM. Let's plug in our values. The key for the HMAC function is our salt, random salt. The data for the HMAC function is our IKM, shared secret. When we compute this, the HMAC-SHA-256 function will produce a 32-byte output, which is our PRK on the slide. You can see the exact 32-byte hexadecimal value that results from this operation. This is our new, high-entropy master key. HKDF expand setup. Now that we have our PRK, we can proceed to the expand step. Our goal is to generate a total of 28 bytes of keying material. 16 bytes for the AES key and 12 bytes for the IB, since our hash function, SHA-256, produces an output of 32 bytes. A single iteration of the expand step will be more than enough to get the material we need. This means we only need to calculate one block, T1. If we needed more than 32 bytes, say 40 bytes, we would need to calculate a second block, T2, and concatenate the results. HKDF expand calculation. Let's calculate our first and only block, T1. The formula is T1 equals HMAC-SHA-256, PRK, info, or 0x01. The key for this HMAC operation is the PRK we just calculated in the extract step. The data is our info string, AES 128 GCM key IV, concatenated with the single byte 0x01. Plugging these values into the HMAC-SHA-256 function gives us a new 32-byte result. This result is our T1 block. Since this is the only block we need, this 32-byte value is also our final output keying material, or OKM. Slicing the OKM. We've successfully generated 32 bytes of high-quality keying material. Our OKM now for the final, simple step. Slicing it up to get our key and IV. Our goal was a 16-byte key and a 12-byte IV. So, we take the first 16 bytes of the OKM, and that becomes our AES encryption key. Then, we take the next 12 bytes of the OKM, and that becomes our IV. We have 4 bytes left over at the end, which we simply discard. We have now successfully derived a unique, purpose-bound key and IV from our original shared secret. Example summary. Let's review what we just did. We started with a low-entropy shared secret and a salt. We fed them into HKDF extract to produce a single, 32-byte, high-entropy pseudorandom key, PRK. Then, we used that PRK as the key for HKDF expand, along with a context-specific info string, to generate 32 bytes of output keying material, OKM. Finally, we sliced that OKM to get our 16-byte key and 12-byte IV. This two-step process transformed our simple inputs into secure, independent cryptographic keys ready for use. The TLS 1.3 Key Schedule Overview. Now that we understand the extract and expand mechanics and have seen an example, let's see how TLS 1.3 uses them in a beautiful, cascading key schedule. The entire process is a series of HKDF operations that evolve the secret state of the connection from an initial shared secret into all the keys needed for secure communication. It begins with the secret from the ECDHE key exchange. This is used to derive a handshake secret. The handshake secret is then used to derive a master secret. And finally, the master secret is used to derive the application traffic secrets, which in turn produce the final keys that encrypt your data. It's a carefully designed flow that ensures security at every stage of the connection. The importance of transcript hashes. Before we dive into the specific keys, we need to understand a critical concept, the transcript hash. As the client and server exchange handshake messages, such as client hello and server hello, and so on, both sides are constantly hashing the conversation as it happens. This running hash is called the transcript hash. As we saw in the HKDF label structure, this transcript hash is included as the context in the info parameter for every key derivation. This is an incredibly powerful feature. It cryptographically binds every key to the exact sequence of messages that came before it. This means an attacker can't splice messages from another session or change the handshake parameters, because doing so would change the transcript hash and result in the server and client deriving completely different keys, causing the connection to fail immediately. The handshake secret. The key schedule kicks off right after the client and server have completed their Diffie-Hellman exchange. The very first derivation step uses HKDF extract. The input keying material, or IKM, is the shared secret from the ECDHE exchange. The salt for this initial step is a previously derived secret, but at the very beginning of the handshake, it's just a string of zeros. This HKDF extract operation produces the first major key in our schedule, the handshake secret. Its purpose is to derive keys that will protect the remainder of the handshake messages, such as server certificates and authentication messages. Stage 2. Handshake traffic keys. With the handshake secret in hand, we now need keys to actually encrypt the handshake messages. For this, we use the HKDF expand step. The handshake secret we just created is used as the PRK, which is the key for the HMAC function. We then run HKDF expand twice with two different info labels. One label, such as CHS traffic, client handshake traffic, is used to generate the key and IV for encrypting handshake messages sent by the client. Another label, SHS traffic, is used to generate the keys for messages sent by the server. This ensures that the client and server use different keys, even at this early stage. The transcript hash up to this point is included in the info label. The master secret. Once the handshake messages have been securely exchanged, the protocol transitions to creating the keys that will protect the application data. This is achieved by evolving the secret state once again. A new HKDF extract operation is performed. This time, the IKM is a derived value, and crucially, the salt is the handshake secret from the previous stage. This operation produces the most important key of the session, the master secret. By using the handshake secret as the salt, we cryptographically bind the new master secret to the entire handshake that just occurred. This is a key step in the security of the protocol. Stage 4. Application traffic keys. We have now reached the final stage of key derivation for the main communication. The master secret becomes the PRK for a new set of HKDF expand operations. Just as with the handshake keys, we generate separate keys for the client and server. Using an info label like CAP traffic, client application traffic, we derive the key and IV that the client will use to encrypt the data it sends to the server, like an HTTP GET request. And with the label SAP traffic, we derive the key and IV that the server will use to encrypt its responses. These are the keys that protect the core content of your web session. The full handshake transcript hash is included in these labels. Stage 5. The resumption secret. TLS 1.3 also has a feature for resuming sessions quickly, known as 0 RTT, or 0 round trip time, data. To do this securely, it needs another key called the resumption master secret. And how is this key created? You guessed it, HKDF. The resumption master secret is derived from the master secret using another HKDF expand operation with a specific info label like res master. This secret can then be used in a subsequent connection to derive 0 RTT encryption keys, allowing the client to send encrypted data in its very first message, speeding up the connection. HKDF's flexibility makes it perfect for deriving these specialized keys as well. The exporter secret. Sometimes, an application built on top of TLS needs to derive its own keys that are tied to the TLS session, for example, in the QUIC protocol. Doing this naively could be dangerous and might compromise the main traffic keys. To solve this, TLS 1.3 provides a safe mechanism using an exporter secret. This is yet another secret derived from the master secret using HKDF expand with a label like Express Master. This exporter secret is not used for TLS's own traffic but is instead exposed to the application layer. The application can then use this as an input to its own KDF to derive context-specific keys, without ever touching the keys that protect the main TLS traffic. Full key schedule diagram. This diagram shows the complete, beautiful cascade of key derivations in a TLS 1.3 handshake. It all starts with a single point of shared entropy from the Diffie-Hellman exchange. The first HKDF extract produces the handshake secret, which is expanded to create the handshake traffic keys. Then, another HKDF extract uses the handshake secret to produce the master secret. From this central secret, we branch out using HKDF expand to create all the necessary keys for the connection. The application traffic keys for protecting data, the resumption secret for future sessions, and the exporter secret for the application layer. Every arrow in this diagram represents a carefully defined HKDF operation, creating a robust and secure key hierarchy. Security property. Key independence. Let's revisit the security properties with this full context. Key independence, also known as key separation, is paramount. Because every key is derived with a unique info label, they are all cryptographically independent. If an attacker were somehow able to compromise, for instance, the client application traffic key, it would tell them absolutely nothing about the server's key, the master secret, or any other key in the schedule. Each derivation is a one-way street, and the unique labels ensure they lead to different destinations. Security property. Entropy concentration. The initial shared secret from a Diffie-Hellman exchange is a large number, but it is not guaranteed to be perfectly uniform or random. There might be some mathematical structure or bias. The very first HKDF extract step acts as a purifier. It takes this potentially non-uniform IKM then, through the magic of the HMAC function, it concentrates its entropy into the PRK. This ensures that the foundation of our key schedule is as random as possible, making all subsequent derivations more secure. Security property. Domain separation. Domain separation is the formal term for preventing keys from one context being used in another. HKDF provides this at two levels. The salt in the extract step separates different uses of the same IKM. For instance, two different protocols could use the same shared secret but different salts, and their entire key schedules would be independent. Internally, the info parameter in the expand step provides domain separation for each key. This is what keeps the client's handshake key from being confused with the server's application key. This careful separation is a cornerstone of modern cryptographic engineering. Security property. Forward secrecy. While forward secrecy primarily comes from using an ephemeral key exchange like ECDHE, the TLS 1.3 key schedule is designed to maintain it. Forward secrecy means that if a server's long-term private key is compromised in the future, it cannot be used to decrypt past, recorded sessions. Because each session starts with a fresh ECDHE exchange, a new and unique IKM is created every time. This IKM is used to derive all the session keys and is then discarded. The server's long-term key is only used for signing the handshake to prove its identity. Since the session keys are derived from the temporary secret, not the long-term one, the compromise of the long-term key has no effect on the confidentiality of past traffic. Why not just use a hash function? A common question is, why do we need this complex HKDF process? Why not just do something simpler, like key 1 equals SHA-256 open parenthesis secret or 1 close parenthesis and key 2 equals SHA-256 open parenthesis secret or 2 close parenthesis? While this seems plausible, it has weaknesses. Standard hash functions are not designed to be used as KDFs, and can be vulnerable to attacks like the linked extension attack when used with a secret prefix. HKDF's use of the HMAC construction fundamentally prevents these issues. The HMAC algorithm was specifically designed to handle secret keys securely, providing much stronger guarantees about the unpredictability and independence of its outputs. The formal security proofs of HKDF rely on these properties of HMAC, providing a level of confidence that ad hoc constructions simply cannot match. HKDF versus PBKDF2. You might have heard of another KDF called PBKDF2. This stands for Password-based Key Derivation Function 2. It is important to understand that they are designed for different problems. PBKDF2 is designed to take a low-entropy input, like a human memorable password, and make it very slow and expensive to hash. It does this by iterating a hash function thousands of times. This slows down brute force guessing attacks. HKDF, on the other hand, is designed for high-entropy inputs, like the output of a Diffie-Hellman exchange. Its goal is not to be slow, but to be efficient while securely extracting and expanding that entropy into multiple keys. You would use PBKDF2 for password storage, and HKDF for protocol key derivation. Key update mechanism. Even after the handshake is complete and application data is flowing, TLS 1.3 has a mechanism to update the keys for the connection. This is useful for very long-lived connections to ensure that not too much data is encrypted with a single key. How does it do this? With HKDF, of course. A key update is triggered, and a new application traffic secret is derived from the current one using HKDF expand with a label like traffic update. This evolves the secret state forward, creating a new generation of keys. This new secret is then used to derive the next set of application keys, and the old ones are discarded. This can happen multiple times within a single connection, enhancing security. The simplicity of the cipher suites. One of the major benefits of using HKDF is that it dramatically simplified the concept of a cipher suite in TLS 1.3. In TLS 1.2, a cipher suite defined the key exchange method, the authentication method, the symmetric cipher, and the key derivation function, PRF. It was a complex combination. In TLS 1.3, because HKDF is used for all key derivation, the cipher suite only needs to define the symmetric cipher, like AES-GCM, and the hash function to be used with HKDF, like SHA-256. This reduced complexity makes the protocol easier to implement correctly and less prone to errors. Implementation considerations. When implementing protocols that use HKDF, it is critical to use a well-vetted, constant-time cryptographic library. A constant-time implementation means that the code takes the same amount of time to execute regardless of the inputs. This is crucial to prevent timing side-channel attacks, where an attacker could learn information about the secret keys by measuring tiny variations in how long the cryptographic operations take. Luckily, all major cryptographic libraries like OpenSSL, BoringSSL, and libsodium provide secure, constant-time implementations of HMAC and HKDF, so developers can build on this solid foundation without having to become experts in preventing side-channel attacks themselves. HKDF beyond TLS. While our focus has been on TLS 1.3, HKDF's utility extends far beyond it. It is a general-purpose KDF used in many other modern cryptographic protocols. For example, the Signal protocol, which provides end-to-end encryption for messaging apps like WhatsApp and Signal, uses HKDF extensively in its key ratcheting mechanism. The QUIC protocol, which is the underlying transport for HTTP3, also uses HKDF in a manner very similar to TLS 1.3 for its own key schedule. Any protocol that needs to derive multiple keys from a shared secret can benefit from HKDF's simple, secure, and flexible design. The future. Post-quantum KDFs? As we look towards the future and the eventual arrival of quantum computers, the cryptographic landscape will change. The asymmetric algorithms currently used for key exchange, like ECDHE, will be broken. They will need to be replaced with new, quantum-resistant algorithms. However, the symmetric parts of our protocols, including hash functions, HMAC, and by extension, HKDF, are believed to be much more resilient to quantum attacks. It is likely that even in a post-quantum world, we will still use a KDF like HKDF. The only change will be the source of the IKM. It will come from a new, post-quantum key exchange algorithm, but the process of extracting and expanding it into session keys will probably look very familiar. Final takeaways. Let's summarize the key takeaways from our deep dive. First, never use a single secret for multiple cryptographic purposes. You need a key derivation function. Second, HKDF is the modern, standardized KDF used in TLS 1.3 and other protocols. Third, its strength comes from the two-step extract then expand design, which purifies the initial secret and then safely generates multiple, independent keys from it. Fourth, the use of HMAC as the underlying primitive provides strong security guarantees. And finally, the use of context-specific infolabels is critical for binding keys to their intended purpose, which prevents a wide range of attacks. What we've learned. We have journeyed through the elegant mathematics that secure our digital world. We saw how TLS 1.3 leverages the powerful, two-stage HKDF process to transform a single shared secret into an entire hierarchy of keys. It starts with HKDF extract to concentrate randomness into a powerful pseudorandom key. Then, the HKDF expand step uses this key iteratively to generate a multitude of purpose-built, independent keys for every stage of the connection, from the initial handshake to the application data, and even session resumption. This robust and proven mechanism is a cornerstone of modern cryptography, working silently in the background to ensure our online communications remain private and secure. Thank you. This brings us to the end of our detailed exploration of HKDF. We've gone from the basic need for session keys, through the mechanics of hashing and HMAC, into a detailed, worked example, and finally through the entire key schedule of the most important security protocol on the Internet, TLS 1.3. I hope this presentation has demystified the process of key derivation and given you a deeper appreciation for the elegant engineering that keeps us safe online. Thank you for your attendance. Please consider subscribing to the channel.